this video lecture, let's try to utilize our weak form with Galerkin method and try to come up with an approximate solution that makes sense. Okay, so let's consider this differential equation here, which is uxx plus 2x is equal to 0. X is defined over the domain going from 0 to 1, which essentially means that your length of the domain is 1. Okay, and 2x represents the distributed force. So your f of x in your generalized PDE that we have discussed previously is equal to 2 times x. Okay, and then we have two sets of boundary conditions. U at x is equal to 0 is 0, and derivative of u with respect to x at x is equal to 1 is also 0. So can you tell me what type of boundary conditions these are? And hopefully you guessed it right. So the first one is our essential boundary condition, and the second one is our natural boundary condition. Okay, so let's go ahead and try to come up with a weighted residual form. Which would equal to some weight function times uxx dx plus integration of weight function times 2x dx is equal to 0. Okay, and we can write a weak form as negative of integration wx ux dx plus w times ux over the boundary plus integration of w times 2x dx is equal to 0. Okay, now note that we have essential boundary conditions at x is equal to 0. Okay, that implies that our weight function at x is equal to 0 is also 0, and natural boundary condition at x is equal to 1 implies that ux at 1 is 0, which comes from our boundary condition right here, right? So following these two, if we take our boundary evaluations, we'll end up having 0. Okay, and you can try to work this out on your own. So then we'll end up with a weak form that looks like integral of w comma x ux dx is equal to integral of 2 times wx dx. Now assume that our approximation looks something like this: phi0 of x plus c1 phi1x plus c2 phi2x and so on, right? So since we have essential boundary condition defined as such, we can then say that our phi0 of x that only has to satisfy our essential boundary condition is also equal to 0. Okay, then we end up with our u of x is equal to c1 phi1 x plus c2 phi2 x and however many terms we want. Okay. Now for these phi i's, there are some requirements that needs to be followed. Okay. The phi i's need to be 0 at the essential boundary conditions. So in our case, at x is equal to 0, our phi i's should be 0. Okay. In the second, the phi i's should be differentiable at least once. Can you tell me why the phi i's should be differentiable at least once? Hopefully you got it right. The phi i's needs to satisfy the weak form, right? And since we are requiring the first derivative of the u, we also require the first derivative of our functions phi1, phi2, etc. Okay. So now, following this, let's assume a one parameter solution. Which is u of x is equal to c1 times phi1 of x. Okay. And for phi1 to satisfy these two requirements, let's say our phi1 x is equal to x, and if we see that that's x is differentiable at least once, and it will be 0 at x is equal to 0, so it will also satisfy our prerequisite of being 0 at essential boundary conditions. Okay. So then we can write our u of x is equal to c1x. Okay. Now applying Galerkin method, we can say that we want to solve for, we can say that our weight functions are is equal to phi I, right? So in this case, we only have one coefficient to solve for. So we only need one equation, right? So then our weight function is equal to x. Okay, so let's consider our weak form again. Integration from 0 to 1 wx ux dx is equal to integration from 0 to 1 w times 2x dx. Now for convenience, let's write down our differentiation of w with respect to x, which would be 1, and differentiation of u with respect to x, which would be equal to c1. Okay, so applying Galerkin method, we can then write that wx is simply 1 times ux is c1 dx is equal to integration of 2 times w is x times x dx, and simplifying this we end up with C1 is equal to 2 times x cubed by 3 evaluated over the boundary 0 to 1, which is simply 2 by 3. Okay, and that results in our approximate solution, which would be 2 by 3 times x. Okay, so this is our one parameter solution. Now we can see that from the one parameter solution that the solution is not representative of the exact solution, and if you were to compare them side by side, you will probably see large errors in the profile of u of x versus x. So to remedy this situation, we can add more parameters to our approximate functions. So instead of considering one parameter, we can assume a two-parameter solution. Such as u of x is equal to c1x plus c2x squared. Okay, remember that we already got rid of phi 0 of x, which is set to 0, right? So we are only considering terms phi i's here. Okay, so then I can write ux is equal to c1 plus 2 times c2x. Okay, with Galerkin method, we will have our first weight function is equal to x, and then w1x is equal to 1. So then plugging that into our weak form, we can get 1 times ux, which is c1 plus 2c2x dx, is equal to w, which is x times 2x dx. Okay, simplifying this, we'll end up with c1 plus c2 is equal to 2 by 3, and let's call this equation number 1. Okay, now consider our second weight function w2 is equal to x squared. Then we can write w2x is equal to 2x. Okay, and we end up with another equation, which is wx, which is equal to 2x times c1 plus 2c2x dx is equal to integration from 0 to 1 of x squared times 2x dx. And simplifying this, we'll end up with c1 by 2 plus 4 by 3 c2 is equal to 1 over 2. Okay, now we have two equations. We have two unknowns, c1 and c2, which we can solve by writing it into a matrix form. So I can write the coefficients of c1 and c2 from the first equation to be 1, 1, and the second row will be coefficients of c1 and c2 from the second equation, which would be 1 by 2 and 4 by 3 times c1 c2 is equal to 2 by 3 and 1 by 2. Okay, solving for this, we'll end up with C1 is equal to 0.2 and C2 is equal to 0.4667. Okay, and I'll leave that for you to verify. Okay, so then we can write our two parameter solution. U of x is equal to 0.2 times x plus 0.4667 times x square. This is our two parameter solution. At this point, we can see that it still doesn't represent the exact solution. Okay, so in order to get an approximate solution that is close to an exact solution, we will need to use more than two parameters. Okay, so we could, for example, go with a three parameter solution, such as c1x plus c2x square plus c3x cube, and more. So more parameters or more functions we use, better the approximation. So here I have plotted various approximate solutions that we have obtained so far, and compared it with the exact solution. So here in red, our exact solution. The curve in blue is our one parameter solution, in green is our two parameter solution, and in the blue dots is our three parameter solution. Okay, and as you can see, as we include more and more parameters to our approximate solution, we get a solution that is more close to our exact solution.